Dear students, in previous classes we have studied that in purely resistive circuit, voltage and current are in phase. In purely inductive circuit, current lags the supply voltage by 90°, and in purely capacitive circuit, current leads supply voltage by 90°. Now if both resistance and inductance are there in the circuit, then what happens? Or if both resistance and capacitor are there in the circuit, then what happens? That we will study. Recap. In purely resistive circuit, supply voltage and current are in phase. In purely inductive circuit, current lags voltage by 90°. In purely capacitive circuit, current leads voltage by 90°. I'll write here RL series circuit and RC series circuit. With all same notations for resistance, inductance and capacitance. We can draw here RL and RC series circuits. Supply voltage V equal to Vm sin omega t is supply voltage. Here also V equal to Vm sin omega t is supply voltage and I is supply current. When both R and L are there in the circuit, then current in the circuit will be lagging the supply voltage by less than 90 degrees. So current I expression may be written as Im sine of omega t minus phi, where Im is equal to Vm by Z, where Z is impedance and Z is equal to under root R square plus XL square. In capacitive circuit, current I is equal to Im sine of omega t plus phi, because in capacitive circuit current leads supply voltage by an angle less than 90 degree. So here phi is less than 90 degree, where Im is equal to Vm by Z, where again Z is impedance and impedance Z is given by R square plus XC square. Now we can draw the waveforms for these two circuits. Voltage waveform starts at 0 radians in both the circuits. So this is V here and this is also V. Current lags supply voltage by an angle less than phi. So I can show current lagging the voltage by angle phi, whereas in case of capacitive circuit, current leads the supply voltage by 5 degrees. So here we can show current leading supply voltage by 5 degree. Now this waveform is for instantaneous current I, and here also This waveform is for instantaneous current I. Now for both the circuits, we can draw instantaneous power curve. From 0 to 5, voltage is positive and current is negative. Therefore, the product will be negative. And from 5 to pi, both voltage and current are positive. So the product will be positive. From pi to pi plus 5, voltage is negative and current is positive. So again the product will be negative. From pi plus 5 to 2 pi, both voltage and current are negative. Therefore, the product will be positive. Similarly, we can draw remaining part of the power curve. This way. And here, this is minus 5 here, 0, here it is pi minus 5, this is pi, this is 2 pi minus 5, this is 2 pi, this is 3 pi minus 5, and this is 3 pi. From minus 5 to pi, current is positive, and if we extend the voltage, voltage is negative. And when we multiply, the product becomes negative. That is, instantaneous power is negative here. From 0 to pi minus 5, both voltage and current are positive. So the product will be positive. From pi minus 5 to pi, current is negative and voltage is positive. So the product will be negative. Similarly, we can continue and draw the remaining part of power curve. This way. So in both these cases, we can see that positive power is more than negative power in each half cycle. Therefore, the power taken by RL series circuit from the source is more than the power returned to the source, which means that RL series circuit, similarly RC series circuit consume certain definite power, and those powers are given by power P equal to Vrms IRMS into cos phi. Here also power P equal to VRMS into IRMS into cos phi. Cos phi is called as power factor. Power factor is defined as ratio of resistance to impedance of circuit. That is cos phi equal to R by Z. In inductive circuit, Z is R square plus XL square under root, and in capacitive circuit, Z is R square plus XC square under root. For RC and RL series circuits, cos phi is less than 1. Therefore, P is less than VRMS into IRMS. VRMS into IRMS is called as apparent power. So we'll write the definition for apparent power. It is the product of RMS voltage and RMS current supplied to the circuit. It is denoted by capital S. Its unit is volt ampere, or in short VA. Reactive power it is the product of RMS voltage RMS current and sin phi it is denoted by capital Q. Its unit is volt ampere reactive, or VAR. So we can write here apparent power S as Vrms into Irms and reactive power Q as Vrms into Irms into sin phi. Squaring and adding P and Q, we get P square plus Q square equal to Vrms into Irms into cos phi whole square plus Vrms into Irms into sin phi whole square. So Vrms into Irms square inside the bracket cos square phi plus sin square phi. Taking square root on both sides, we get Vrms into Irms into 1, that is P square plus Q square equal to Vrms into Irms. And we know that Vrms into Irms is apparent power S. Therefore, we can write S equal to under root P square plus Q square. Phasor representation of voltage and current in RL and RC circuits. In RL series circuit, Irms lags Vrms by 5 degrees. And in RC series circuit, Irms leads Vrms by 5 degrees. Impedance phasor diagrams. we'll have here a line which divides capacitive circuit and inductive circuit. We are having Z is equal to R square plus XL square under root in inductive circuit, and Z equal to R square plus XC square under root in capacitive circuit. So using Pythagoras theorem, we can show this impedance as a triangle formed by three phasors, namely impedance phasor, resistance phasor and inductive reactance phasor. Similarly in RC series circuit also. R and Z are at 5 degrees to each other, and XL is shown at 90 degrees to resistance R. In capacitive circuit, XC is shown at 90 degree to resistance but below resistance phasor. And Z is nothing but hypotenuse phasor and is at 5 degree to R. In the same way, we can draw power phasor diagram also. Again, we will have here a division for RL circuit and RC circuit. We know that S equal to under root P square plus Q square. Here also S is equal to under root P square plus Q square. In inductive circuit and capacitive circuit, P is taken as reference phasor and in inductive circuit Q is shown below reference at 90 degree to P. Whereas in capacitive circuit, Q is shown at 90 degree to P but above reference. The hypotenuse now becomes apparent power and is at 5 degree to P. In case of inductive circuit, also S is hypotenuse and it is at 5 degree to real power P. Now we will define what is real power or true power or active power. It is for all circuits. Real power or true power or active power. It is the power consumed by any electric circuit to do certain work. It is denoted by capital P. Its unit is watts. It is calculated as P equal to Vrms into Irms into cos phi. I have already told you RMS voltages may be denoted by capital V or capital I only, or with subscript RMS. In case of purely resistive circuit, cos phi is 1, therefore power will be equal to V into I. And in case of resistive and inductive circuit, cos phi value will be less than 1. So, real power or true power or active power in inductive or capacitive circuit will be less than product of Vrms and Irms.